Okay, so we're going to look at a PSPACE complete problem. And so last time we talked about fully quantified Boolean formula. Okay, a fully quantified Boolean formula is a Boolean formula where each variable has a quantifier. Okay, so either it is an existential quantifier or a universal quantifier. For instance, in this case, we have an example that this is a fully quantified Boolean formula because it has two variables and each variable has a quantifier. For instance, here x has a universal quantifier and y here has a existential quantifier. So then each fully quantified Boolean formula will either be true or false. Okay, so it's always either be true or false. So this is different from unquantified Boolean formula where we talk about satisfiability. So whether you can find a truth assignment for the variables to make that formula true. So in that case, that's satisfiability. In this case, we don't have that concept because each fully quantified formula will either be true or false. So now we put all the true fully quantified Boolean formulas into a set. Okay, so then we call that TQBF. So T stands for true. Okay, so true fully quantified Boolean formula, which is a set of the set of encodings of Boolean formula that is fully quantified and it's true. And then this set is PSPACE complete. So in other words, it is the hardest problem in PSPACE. So what we are going to prove, so this is a proof. So we first prove that TQBF is in PSPACE, okay? So which of course is quite straightforward because we only need to look at three things. Okay, so this is how we determine that TQBF is in PSPACE, meaning that we have a deterministic Turing machine that accepts this set TQBF in polynomial space. Okay, so actually TQBF can be accepted by a deterministic Turing machine in linear space. That, of course, is a polynomial. So this Turing machine takes an input, so that is encoding of a fully quantified Boolean formula. And then we check to see whether Q contains quantifiers or not. So the case one says that this formula phi doesn't contain quantifiers. So that means that it doesn't have variables. Because we know it has to be fully quantified, that if it has variables, it must have a quantifier for that variable. And if it doesn't have, that means there is no variables. Then, of course, it will either be some constants connected by logical operations. So that means you can evaluate it to be either true or false. Okay, so this is easy. Then then you look at the first, you look at so this phi would start with a sequence of quantifiers. So if the first one is an existential quantifier, then you can just assign 0 and 1. That means false and true to x. If one of those is evaluated true, then you accept it. Otherwise, you reject it. You reject this formula. Similarly, if the first one is for all x, then you assign 0 and 1 to x and accept this formula if both of them accepts. So this is straightforward to evaluate. So what you need to do is to, now this is a recursive function. So what you need to do is to remember your choice, right? So whether you put 0 or 1 in it. So you have, let's say you have m variables. Then of course, each variable can either be true or false. So for each recursive call, then the space you need is just the space you need under that particular choose assignment to evaluate that formula. So that is a linear time. So that is quite straightforward. Okay, so then next we're going to reduce any language in PSPACE to TQBF. So for this purpose, so let A be a language decided by a deterministic Turing machine, M in space, n to the k for some constant k, because it says a polynomial. Okay, so then we're going to reduce A to TQBF. So the construction is similar to Savage's theorem that we talked about last time. Okay, so how do we use a deterministic Turing machine to simulate non-deterministic Turing machine using quadratic space? So this is similar. So what we are going to look at here is that since A is accepted by M, so that really means that for any string W, okay, so we are going to construct a Boolean, a fully quantified Boolean formula to represent a computation history of M on input X. And we want to make sure that Boolean formula we constructed will be within a polynomial space of M, which is your encoding, and X or W. So that's what we want to make sure. Okay, so then since we are going to simulate a computation history, we know that, so M on W will start from an initial configuration, and then you go to this next configuration. So let me use the arrow key here. So C1 go to C2, and go to, so when it accepts, so let's say L. So go to CL. CL is a halting state. Okay, so then M accepts W. That means that there is a computation path. You start from the initial computation path and ends a accept path. So that means that C1 goes to CL in T steps. Okay, so this T is at most, as we know that the total number of different configuration is at most, so let me write it here. So T here is at most 2 to the T times n to the k. Okay, so this is n to the k. So if we call that as f of n, so that's 2 to the d to the f of n. So that's how big T is. So then what we are thinking about here is that M accepts W. So let me put it here. So M accepts W if and only if, okay, C start okay, and can go to C accept in T steps. Then since we know how to represent a computation history by a formula, so that means if and only if, let's say we use this formula, C star, C accept in T steps. Okay, however then, this formula may be too long because T is big. So T is this big. So T is too big. Okay, so even though you can try to use a using Savage theorem, you can try to use by having, no, this is a Boolean formula, so we use existential quantifier for a variable. So that means I can go from C1 to M1 in T over 2 steps, and I can go from M1 to C2 in T over 2 steps. But this, since the T is big, so this formula will be too long. Too long means that it's longer than a polynomial. So then that defies our purpose. So instead, the trick to overcome this problem is to use a universal quantifier. So that is actually, we don't want a formula that consists of 2 parts. Instead, I just want to use a single part. So in order to represent that 2 parts in the earlier slide, right? So it's 2 parts. What I do is I use a universal quantifier to indicate that's it's going to be the 2 parts. So that means that there exists M1 such that for all configurations, C3 and C4, which means that either C3 is C4, and for all, that means C3 is C1 and C4 is M1. And and then we have this C4 here that is M1, and then this is C2. So for all of these, you can go from C1 to C4 and from C4 to C2. Okay, so this is because it's already C1. So I mean, that means for any for all C3 and C4, that you can go from C3 to C4 in half of the steps. So that represents the earlier 2 formula here. Okay. So then the next thing we need to worry about here is that for this particular form, we could use a formula to represent to get rid of this for all something in a set, right? So this is how it is done here. So for all x in yz followed by a formula, it is equivalent to for all x is equal to y, or x is equal to z implies, and then the same formula here. So it's the same formula here. So that is in the form we are looking for. So this is a fully quantified Boolean formula. So that's it. Then we know that this Boolean formula, the length of it will be log of 2 to the t and k. So that is d and k. So this is, so the length of this formula is polynomially bounded. And that's a reduction. So pretty straightforward here. So that is a proof. So this is a lot easier when we talk about this reduction, then we talk about SAT is NP complete, because now when we talk about SAT, we talk about how to use a Boolean formula to represent a computation history. So right now we just need to include quantifiers to represent a computation history. So that is the proof. Okay, so next we are going to extend this to look at another problem, which is PSPACE complete. And this is a two-player formula game. This is really just like TQBF, but we change the setting a little bit to make it more interesting. So what you are given here is a fully quantified Boolean formula. Okay, Q1, Q2 up to Qk are quantifiers, and you have k variables in this formula. Okay, so this is this Boolean formula phi in this form is called premix normal form. Now we have two players. One is called player E for existential quantifiers. The other one is a player A for universal quantifier. So they take turns selecting the values of the variables, x1, x2. So this is Q1 and excuse me. So these two players will take turns to selecting the values of the variables. Of course, then the order of play is the same as that of the quantifiers at the beginning of the formula. So if this is a universal quantifier, player A plays first. If this is Q1 is existential quantifier, then the player E plays first. So that's what this means. So at the end of the play, we use the values that the player have selected for the variables. So that means at the end of the play, then we have a choose assignment. So that means that we can evaluate the formula under that choose assignment. And if okay, so this should be psi. Okay, so this is a Greek letter psi. So this is a formula. So under this particular choose assignment selected by this player, if it's evaluated true, okay, then player E won the game. Otherwise, player A wins the game. So player A wants to select variables, to select values for the variables to make the evaluation of this formula false, and player E wants to make it true. So that's how they play this game. And then this is NP-hard problem. This is a PSPACE complete problem. So here's an example to see how this game is played. So we let phi 1 be the following. There exists x1 for all x2, exists x3 such that this is true, right? So that's what this means. So then, because it begins with is an existential quantifier, so player E plays first. So let's say he picks x1 to be 1. Then player A here, now because x1 is 1, then this is true. But then, so these two, he doesn't know. So then because player A wants to make it false, so then he will pick, player A then will pick x2 to be false to make this, hopefully to make this false. But then of course, when it's turn for player E, he can pick x3 to be true. So in that case, then this formula, after you strip off these quantifiers, this formula under that choose assignment x1 1, x2 0, and x3 1 is evaluated to be true. So then of course E wins in this game. So if you look at the second example, we change the Boolean formula a little bit. So get rid of this x2 bar. So we put x3 bar here. Then in this case, the player A has a winning strategy. Okay, so for simply by selecting x2 to be 0. So if it's 0, 0, and 0 here, so no matter how x3 is picked, one of these clause will be evaluated. So one of this and that will be evaluated to false. So that means that phi 2 will be evaluated to false, as long as player A selects x2 to be 0. So then player A has a winning strategy for this game. So then we want to know, for a given formula like this, we want to know whether player E has a winning strategy. And likewise, we want to know whether player A has a winning strategy, right? So this is symmetric. And this problem is PSPACE complete. Okay, so first of all, we just need to prove that we can reduce TQBF to this problem. Okay, so this formula in this appendix normal form is true when some setting for x1 exists such that for any setting of x2, a setting of x3 exists such that, and so on, right? So for some selection of x1, then no matter what x2 is, and then for some selection of x3, no matter what x4 is, blah, 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 right? So to make it true. So that is so that is when player E has a winning strategy. Okay. So then we can see that this is really just TQBF, right? So this itself is just a TQBF because we want to evaluate it to be true. So then the reduction really is quite straightforward. So that means that Q is in TQBF. So this particular Q, that's evaluated is evaluated true exactly when this is in this formula game. Okay, so that is a second PSPACE complete problem. So in your homework, I asked you to look at a man-made problem which depends on Turing machines halting problem to be also PSPACE complete. So now let me summarize what we did here. So the goal, we look at resource-bounded computation is first, of course, we know that this is what computer scientists are interested in, because in the second part, we look at computability, right? So that is, that doesn't have a resource bounds. But for us, even if something is decidable, we still want to know how fast or how much space is needed, how fast we can compute and how much space is needed. So that we need to look at time complexity and space complexity. And it happens that in reality, there are many problems that when you try to find efficient algorithms to solve them, and all the efforts so far have failed. Okay, so then those problems can be characterized as a problem that they have a polynomial time verification when you present a solution. But then that solution, we don't know how to find, but you can make a guess. So that's why we have these NP complete problems in play. So that is the first one. And then we spend time and efforts to understand or how to show a problem is NP complete. Now we only look at a small number of problems that are NP complete to just get some ideas. And of course, there are many problems in practice that have been shown to be NP complete. Okay, so that is one goal. The other goal is to look at how to look at space complexity, right? So we have time complexity. Now we look at space complexity. And for space complexity, non-deterministic and deterministic space are equivalent within a quadratic polynomial. Okay, so that means that PSPACE is equal to N space, right? So deterministic polynomial space is the same as non-deterministic polynomial space. And then, of course, obviously, space includes NP, right? So PSPACE includes NP. But then we want to know the hardest problem in PSPACE, so that obviously we want to look at a complete problem. Then by putting quantifiers to variables in a Boolean formula, such that each variable has a quantifier. And then we want to know whether that fully quantified Boolean formula is true, is indeed the hardest problem in PSPACE, because we just showed that PSPACE, that problem is PSPACE complete. Okay, so that's it. So that concludes this course. So we have some time left, and maybe I can say a few words about your test 3, which I already said it, I think, last time. So your test 3, again, will be in the same format as test 1, okay? But you may have more true and false problems than test 1, right? So test 1, you have 20% of true and false, and you have multiple answer and multiple choice questions. So this time, because I know that true and false probably will be easier. So then you will have more, but you will also have multiple choice and multiple answer questions. Any questions? Questions? All right then. So your test number 3 will take place on December the 17th, which is the next, I think it's the next Thursday, right? From 6:30 to 9:30. Yeah, so next Thursday. So you have 1 week of time to prepare your final exams. Of course, I'm sure you have other exams. So again, you should look at all the slides and look at all the proofs. You don't need to come up with your own proof, but you do need to know, you do need to understand basic concepts. And when you are presented the proof, you do need to determine whether that proof is correct or not. Okay, so that's what's needed from you. All right, so if you don't have a question, or you don't have it now, then I'm going to stop here. However, I will be online. If you think about something, then you can ask me later. But so in this class time framework, in this time frame. Okay, so
I
you are
have a
free
question.
to. Yeah. Okay. Go ahead.
Are you going to have any office hours this week?
I already have on Monday and Wednesday.
Oh, I mean, like between now and the exam.
Oh yeah, next week. Yeah, next Monday and Wednesday I will have.
Okay, thanks.
Yeah. The same time. So unless you cannot make it, then you will need to send me email. Then we can make an appointment separately.
Okay.
Yeah. Okay. Other questions? Okay then. So you are free to leave, but I will be on here. I will be here just in case you come up with something that you want to ask. I'll be here. Okay. So good luck to your final. Stay healthy and enjoy.
Yeah, thank you.
Yeah.
Professor, just a quick question. So will we have like a review test like this too?
I will, after I have some time, then I will put up maybe sample questions. That's what you ask?
Yes.
Yeah, just like before, that I will put something up there.
Okay. Yeah. Thank you.
Mhm.